All right, so this is part 2 of the bit manipulation lecture. It's mostly exercises that you're going to work along with. So make sure that you understand everything from part 1 before moving on to this part. If you don't, just post up on Discourse and we'll work on that together. Going back to our original question of how a computer adds two numbers. If we represent the numbers as a series of bits in binary, we can then represent the sum as a series of bits as well. So pause the video and see if you can find an expression for an arbitrary yi, so any bit in this result in terms of AI, AI minus 1, BI minus 1 using bitwise operators. The sum and the carry. Now the sum is actually quite easy. So I'm going to write out the sum and the carry separately, the expressions. I'm going to call the carry. I'm going to call the carry for y0, c0. So the sum for y0 is equal to, and let me just bring back the previous content. The sum for y0, and if we look at this side here, is going to be a0 plus b0. We can construct a0 plus b0 by checking if only one of these items is bit level high. And if only one of them is bit level high, we get bit level high as the sum. Otherwise, we get 0. So the sum we can just represent as a0 XOR b0. Then the carry is high only if both a and b are 1. So I can say a0 and b0. Now for y1, we have to consider a1 XOR b1, but part of the sum is also c0. So we would also have to XOR c0. Now constructing c1, we would see if the previous sum, a1 XOR b1, and the carry are all high. That way we would have a carry here as well. So this here represents the sum, and this represents the previous carry, and we're just checking if we have two ones. That would force our current carry to also be high. You should see a pattern starting to emerge, so this would be a2 XOR b2 XOR c1. c2 is a2 XOR b2 and c1. So for any yn the sum is equal to an XOR bn XOR cn minus 1 unless n is 0. And then cn is equal to an XOR bn and cn minus 1, again, except when n is 0. Now we have the relationship between the inputs and their sum and the carry, and I'm going to tell you that this is implemented in hardware as an adder circuit. So taking these two expressions, we're going to draw out what the adder circuit looks like. So the nth bit adder circuit, and you'll have one adder circuit for each bit. Just to remind you that the sum, yn, is equal to an XOR bn XOR cn minus 1, and the carry, cn, is equal to that sum and the previous carry. So drawing that out, an XOR bn, that's this part here. And then we have XOR Cn minus 1, that's this part here, and that gives us our Yn. Next we have Cn is An XOR Bn, which is the result here, and we bring it down, and Cn minus 1 here. And that's how we get Cn. And we would carry this to the next sum. All right, time for another exercise. And you're going to work with a variable of unknown type, var type, y, and you want to count the number of high bits in the binary representation of y using bitwise operators. Using our trusty example 0b01010, the result of this would be 2, because there are 2 high bits, and there's some skeleton for you to work with, so pause the video and then come back and we'll take up the answer. This builds directly off of the bit mask work that we did earlier. I'm going to make a copy of y so that I don't accidentally modify it. Going to make a mask, and this should be an unsigned type. Is equal to 0b01 for now. I'm going to say while temp is not equal to 0. If I sense a high bit, I should increment my counter. And then I should move my bits over, and then repeat. So run through this example 1 or 2 times until you understand the mechanism behind it. You could also shift the mask instead of temp. So work out this alternate solution as well and see how that works. Okay, next exercise. Determine if a number is divisible by 2 using bitwise operations. Okay, so you should recall that if a number is divisible by 2, the least significant bit of that number should be 0, so bit level 0. In our representation of y, if we break it down into its bits, this last term here, in the least significant bit, is 0 or 1, whereas the rest of this are all divisible by 2, because this is 2, the next factor is 4, 2 to the n minus 1 is divisible by 2, 2 to the n is divisible by 2. The only factor that affects our divisibility by 2 is b0. So we only need to enforce that b0 equals to 0 for y to be divisible by 2. Done. So you can then use a bit mask to check if the least significant bit is high. Okay, now consider this scenario. Just take a minute to read this. You have a long sequence of bits and you want to parse the bits in shorter intervals. So for example, in chunks of 8 bits, so chars. And how would you convert X into an array of characters? So I'll give you an example. Let's say you have the starting bits are like so, and this continues down for however many bits a long is. The application of this is actually related to encoding of files. So what is in a file extension or file type? It's really just how the bits are organized in and in what way they should be read and interpreted to reconstruct the data that we have in mind. So in Lab 5, you're going to be working with some type of data that you're going to reconstruct and take meaning out of based on its encoding. As promised, here's the solution for the XOR gate constructed from NOT gates and AND gates. The NOT gates are the circles here. I'm going to trace through that this does in fact work. So starting with A being 1 and B being 0. If I invert 1, I get 0, and here B is still 0, so 0 and 0 is 0. Now working down here, A is 1, B is 0, invert 0, get 1, and 1 is 1. Now I invert 0, invert 1, 1 and 0 is 0, but I invert it and I get 1. So A XOR B for 1, 0 is 1, as expected. For A being 0 and B being 1, invert A, get 1, 1, and we get 1 here, 0 here, 1 inverted, we get 0 here, 0 and 0 is 0, so we actually get just the inverse of the previous case. So then again, we get 0 and 1, 0 and 1 is 0, but we invert it, so we get 1, and then A XOR B is 1 for this as well. Now the case where A and B are both 0, A is 0, B is 0, invert A, get 1, this is 0, so 1 and 0 is 0. Same thing here, we get 0, 1, 0, invert them both, get 1 and 1, 1 and 1 is 1, but invert it, so we get 0. So A XOR B is 0 for 0, 0. Then lastly, for 1 and 1, we invert A, 0 and 1 is 0, then we get 1 here, 0, 0, 1, 1, and then we get 0 here, so A XOR B is 0 again. Done! That concludes our second part of this video. Make sure to ask questions on Discourse and do the additional exercises that have been posted.